Hi, welcome back to Algorithm Strategy class with me, Giaulandari. So in this video, we will start to talk about a technique to solve optimization problem, which is called greedy. This topic will be discussed in 3 videos. So in the first video here, we will talk about the optimization problem, also the grand design of greedy algorithm, and some examples which are coin change problem and also scheduling job to minimize total server use time. In the next video, in part 2, we will talk about 0-1 knapsack problem and also factorial knapsack problem. And then in the third part, we will talk about job scheduling with deadlines and also data compressions. Let's start with what is optimization problem. Optimization problems are problem of finding optimum solution. There are 2 types of optimization. We can have maximization, so we want to maximize something, and also minimization, we want to minimize something. Optimum solution or best solution is a solution that has the best result or value among all possible solutions. So if we are talking about maximization problem, then optimum solution is the best value we have, the maximum value we have. So greedy algorithm is a technique to solve optimization problem. Greedy itself means having or showing an intense and selfish desire for something. So like its name, greedy algorithm tends to take a selfish decision in each step. The main principle of greedy is take what you can get now. So greedy form a solution step by step, where each step you apply this principle. So on each step, the algorithm makes decision on choosing a part of solutions. And a decision that has been made cannot be changed in the next step. The approach used in greedy algorithm is make a decision that looks like will yield best solution by choosing local optimum in each step and also with expectation to reach global optimum. So imagine that we have a start. In the first step, we will see what is the local optimum we have. So that is what we take. And also for the next step until we already found a solution. So greedy in general has 5 components. There are candidate set, solution function, selection function, feasibility function, and also objective function. Candidate set itself is a set whose elements can create a solution. So it consists of elements that can be chosen in each step of greedy algorithm. And solution function is a function that determines the end of iteration. So how can we know that we already found a solution? That is what the solution function do. This function will indicate when we have discovered a complete solution. So we can stop the search and we already found the solution. Next is selection function. So this is the best rule to choose a candidate as a part of solution in each step. We can see this function as a function to determine a local optimum solution. So what can we do to find a local optimum? Next one, feasibility function. It is used to determine whether a candidate can be chosen as a solution. So we already select a candidate based on the selection function, but we may have a constraint such that the candidate is not a feasible solution. So a candidate that is not feasible as a solution at this step can be not considered in the next steps. And the last one is objective function. So this is a function to minimize or maximize the value of the solution. So what are we want from the search? For the first example, we can see a coin change problem. The problem is we have a money of value A and we want to change the money to available coins. But the problem is we want the number of coins that is used to change the money to be minimum. So we want to have a minimum number of coins to change the money with. For example, if we have coins 1, 5, 10, and 25. And also we have money of value 32. We want to change it with these coins. First, we can change it by 30 coins of coin 1, or we can change it to 4 coins of coin 5, 1 coin of value 10, and 2 coins of value 1, so that we can get 7 coins in total. Or we can also have 3 coins of value 10 and 2 coins of value 1, which means we have 5 coins in total. But the minimum number of coins, so the best solution we have for this problem is actually we can have 1 coin of value 25, 1 coin of value 5, and 2 coins of value 1. So in total, we have 4 coins to change the money of value 32. If we solve this problem by exhaustive search, it means that we will need to find all possibilities we have. So we can have a set D1, D2, and so on until the end, where each D represents each coin. It represents 1 coin. So it is a multi-set. D1 and D2 may have the same value, but it is only represent 1 coin. So with exhaustive search, we need to find all possibilities subsets from the multisets. So we will have 2 to the n possible solutions. And computing the number of coins we have can be done in big O n. We just need to find the number of the element of the subsets, right? So it is big O n. Hence, the time complexity of exhaustive search algorithm that can solve this problem is big O n times 2 to the n. But if we have infinitely many coins, because we don't want to care how many coins we have left, then we cannot use brute force because the candidate sets will be infinite. So now let's see how we can solve it by greedy. So previously we have coins with value 25, 10, 5, and 1, for example. And we want to exchange money of value 32. What can we do if we want to have a minimum number of coins to exchange this money? So in each step, if I take 1 first, we will have 31 left. If I have get 5 first, we will have 27 value left. If I take the coin of value 10 first, we will have 22 to exchange left. But if I change it with 25, I will only have 7 value to exchange left. So logically, of course, I will take this first. So I always choose a coins with largest values among all feasible candidates. So back to greedy components. What are the components for coin change problems? The first one, candidate set. Candidate set is the set of elements that we can choose in each step. So here we can have the set of coins that represent the value and the number of available coins. So if I have 5 coins of value 10, for example, then I will have 10, 10, 10, 10, and 10. in the set, and so on. The next one is solution function. Solution function is the function that can let us know when we already found a solution. So we want to exchange money of certain values. So of course we already done if we already got the coins of the total value of the same total value. So the solution function would be the total value of chosen coins is equal to the value of money to change. Next one, selection function. How can we choose a candidate to be a part of the solution? Well, like I said before, we can choose coins that has the largest value from the remaining candidates. Next one, feasibility function. What is the constraint of the candidates to be put in this solution? After we select largest coins, is there any constraint that we need to consider? Yes, the total value of chosen coins cannot larger than the value of money to change. And then the objective function, what we want to have from the search, we want the number of coin to be used is minimum. For example, if we have the same problem as before, we have money of value 32 and also coins of value 1, 5, 10, and 25. So at first we have 30 money of value 32 to change, and because we can change it with 25, the selection function is choosing the largest one first, so we can take 25 first. So we can choose 25 so that we have total value of 25 and we still have money of value 7 to be exchanged. The next one, we check if we can select 25, but based on the feasibility function, we cannot because we only have 7 remaining. So the next one, we check 10. It is not feasible as well. So the next one, we choose 5, which is feasible. So we choose 5 in the next step, so that we have the total value of 30 and the remaining of 2. 25 and 10 is not need to be considered again because we already put it out in the previous step. So we check 5. 5 is not feasible, so we take it out again. So we only have 1 remaining. So in the next step, we choose 1, which is feasible of course, so that we have the total value of 31 and the remaining of 1. So in the next step, we can also choose 1 to have total value of 32, and we already exchanged all of our money, so it means we have found the solution. So the solution we have is the minimum number of used coins is 4, which is indeed the best solution. On each step above, we choose local optimum and yield to global optimum. Mathematically, we can model this coin change problem as the problem when we have a multiset d1 to dn that represents the value of available coins on one element for one coin. And the solution of coin exchange problem can be represented as a tuple like this, where xi is 1 if di is chosen or 0 otherwise. If we want to change money of value a with the available coins, then the objective function will be like this, and the feasibility function like this. And this is the pseudocode for grid algorithm for coin change problems. So we have nothing at first, we haven't chosen any coins yet, and then so we don't have any total value of coins yet. And we search the coins from the largest value first, and we check the constraint, and if it is feasible, then we put it in the solution. But even if it is not feasible, we still take it out from the candidate set. And we update the total value of coins we have if we put the coin in the solution. We end the search if either we already have the total money we have, or we don't have any candidate left. So if we have, in the case if we out of the loop because of this, then we already found the solution. But if we out of the loop because of this, then there is no solution. So in each iteration, we always choose a coin that has the largest value but doesn't exceed the remaining value to change. To have an optimal way in the selection process, we need to sort the coin set in non-increasing order. If we do not consider the time to sort the coin set, then the time complexity of greedy algorithm to solve coin change problem is big O n. However, the effectiveness of greedy for coin change problems is not really good. The greedy algorithm for coin change problem doesn't always yield best solution. For example, if we have coins of value 5, 4, 3, and 1, and we want to change with money of value 7, the greedy solutions means we will choose 5 first, and then we have 2 remaining. We cannot choose 5, 4, or 3, so we choose 1, and then 1 for the last one. So we have 3 coins, but actually the best solution is 4 and 3, which means we only have 2 coins. Another example, if we have coins of value 7, 10, and 1, and we want to change money of value 15. By greedy, we will take 10 first, and then we have 5 remaining. We cannot choose 10 and 7, so we only can choose 5 coins of 1. So we have 6 coins in total. But actually the best solution is we can have 3 coins, 2 coins of value 7 and 1 coin of value 1. In most of problems, greedy algorithm is actually not always result in best solution. This is because greedy does not consider all possible solutions as in exhaustive search, and also greedy does not allow us to change a decision that has been made to improve the solution. The next example is scheduling job to minimize total server use time. So the problem is we have one server to serve end customers, and each customer has fixed time. That is, customer I has service time of TI. How can we schedule the service such that the total server's use time is minimum? To be noted, a customer used the server while waiting and while being served. So customer 1 used the server as many as the waiting time plus the service time. The same with customer 2 and so on until customer n. So the total server use time means use time of all customers we have. Because the service time is constant, we have the fixed one. So the problem of minimizing total server use time is actually the same as minimizing total customers waiting time. The total server use time can be computed like this, like I said before. So it is the sum of the total time customer spent in the system for all customers. For example, I have 3 customers here to be served by one server, and this is the service time for all 3 customers. In exhaustive search, we can search it like this, where we can have a permutations for all three customers. So if customer one is served first, then the customer one only use the server while being served. Then the customer two otherwise use the server while waiting for the customer one to be finished, and also while customer two is being served. And for customer three, uh, customer 3 use the server while waiting customer 1 and customer 2 being served, and also while being served. So the total use time is 38. The same with the next one. This means that customer 1 doesn't have a waiting time. Customer 3 has 5 waiting time, and also for customer 2, the total waiting time is 8. Then after we check all the total server use time for all possibilities, then we can find the minimum total use time, which is obviously this one. So this is the best solution we have. So there are n factorial many possible service order if we consider permutation, because we have n customers. So for the first one, we can put anyone. And then for the second one, we only have n minus 1 customer remaining to be served. And for the third one, we only have n minus 2, and so on until we serve all of the customers. So we have n factorial many possible service order, and computing the total server use time for each order can be done in big O n. The time complexity of exhaustive search algorithm for job scheduling is this one, because we just need to multiply n with n factorial. So by greedy, we want to minimize total waiting time. So logically, of course, total waiting time will be minimum if what we wait is done fast. So customer with least service time will be served first. So the components of greedy we have for job scheduling is the first, candidate set. What can we choose? We choose customers. So the candidate set is set of customers that represent the customers to be served. And solution function. Well, how can we know that we already found the solution? We still need to find the solution until all customers has been chosen. So that is the solution function. Next, the selection function. How can we choose a customer? Like I said before, we can always choose customer with least service time from the remaining customers to serve. So yeah, that is the selection function. The next one, feasibility function. After we choose the customers with the least service time, we don't have any constraint. So there is no feasibility function for this. And then the objective function, what do we want from the search? We want to minimize the total server use time. That is the objective function. So back to the previous example, how can we do it with greedy? So at first we have 3 customers. We haven't served any customer yet. So the total server use time is still 0. So the first time, back to the selection function, we always choose customers with the least service time. So between 5, 10, and 3, of course 3 is the lowest one. So we choose the customer 3 first. We serve customer 3 first. It doesn't have any waiting time. So total server use time is only 3. So we already chose the third customer. So the next one, we choose the next customer, which leads service time, which is obviously the first customer. So the next one, we choose customer one, so that the total server use time is the service time of customer three, what we have in the previous one, and then the waiting time of customer one, and also the service time of the customer one. And we only have customer two left to be served, so obviously we choose it for the next step, so that the total server use time is the service time of customer 3, waiting time of customer 2 plus service time of customer 2 and customer 1, sorry, and waiting time of customer 2 plus service time of customer 2. So the total waiting time, total server use time is 29. So this is the greedy algorithm for job scheduling. Yeah, we can have nothing to choose at first, and then until the candidate set is empty, we always choose customers with least value of TI. So for the algorithm, in each step, we choose customer with the least service time among all remaining customers to serve. We do the iteration until all customers has been served, and to have an optimal way to choose a customer in each iteration, we can sort the customers based on their service time, and of course in non-decreasing order, because we want to choose the least service time first. If we do not consider the sorting time, then the time complexity of greedy algorithm to solve this problem is big O n. And actually, the greedy algorithm for job scheduling to minimize total server use time is always effective, in the sense that we always can find the best solution for it. It is shown by the theorem we have here. So if we have an order such that the service time of the first customer that is served is less or equal to the second, and so on until the last one, then we will have the minimum value of this one, which is the total server use time we want. Okay, that's all for this video, and for the next video we will still talk about greedy, but we will talk about another example, which is knapsack problems. We will talk about both 0-1 knapsack problem and also factorial knapsack problem. Thank you for watching, and see you in the next video.